Let's come back to the phase margin again. We already plot the required characteristics of the border plot for our two-stage op-amp. So it should resemble the first order system. That is, this is the gain bandwidth. So before the gain bandwidth part, we have only one pole. This is what is required. And really in a two-stage op-amp, we have two poles and one zero. And we already derived those zeros, first pole, second pole, DC gain. We already derived those things. So this is the DC gain, ADC. So after that we have first pole. So this slope will be 20 dB per decade. So after that we have gain, this unity gain frequency. Actually the P2, the second pole should come after the gain bandwidth product. So after this second pole we have more slope, this minus 40 dB per decade. After that we have a 0, that is Z1. So after that again we will go to 20 dB per decade. So this is what ideally we want. And the phase plot, we assume initially it is starting from 0. So in the first pole we have a minus 90 degree phase difference, and in the P2 will have 180 degree, minus 180. So during the gain bandwidth product, it will be in between 90 and 180. So if it is very close to 180, our phase margin will be very less. So if it is, the difference is less than 45 degree, that is not acceptable. So generally we prefer for a 60 degree phase margin. Those things we already discussed. So what, in the design point of view, what we have to do to make sure that we are getting at least a phase margin of 45 degree or 60 degree. So we have to derive that relationship. For that, before moving that, we know that if we have P2 here, this is P2. So during P2, this phase will be 180 degree. So if P2 is moving to this side, our phase margin will decrease. So we have to keep P2 away from the gain bandwidth product. And the Z1, that is the 0. This 0 comes after long frequency of after a lot of frequency of gain bandwidth product. So generally we assume that, or we can design 0. We have GM2 and CC, so we can design 0 is greater than or equal to 10 times of gain bandwidth. So this is an assumption. So we keep it as equation 1. And after that we have to find out in what condition we can ensure that 60 degree phase margin. So to get the angle of this, we know the transfer function, that we already derived this transfer function. V out by V in equal to ADC is DC gain into 1 minus S by Z. This is the 0. Then 1 plus S by P1 into 1 plus S by P2. This P1, P2 are the first, P1 and P2 is the two poles. So the angle, we can write the angle of this transfer function, V out by V in equals, ADC is not giving any angles, we can give minus tan inverse omega by Z minus tan inverse omega by P1 minus tan inverse omega by P2. So this will be the angle. So we have to make sure that this angle, by this angle we are getting 60, at least 60 degree of phase margin. To ensure that, we can write this angle V out by V in equals minus tan inverse omega is the frequency by Z minus tan inverse omega by P1 minus tan inverse omega by P2. In the phase plot, I'm plotting it again. So this is P2, this is gain bandwidth, this is P1. Here the 0 comes, and we put the 0 equals 10 times of gain bandwidth. So we can substitute these values here, and we are concentrating at this point. So this is the frequency axis, this is the frequency. So when the frequency is equal to gain bandwidth product or unity gain, what is the phase? What is the phase angle? That is what we are interested in. So we substitute the angle. So here the angle W we substitute with gain bandwidth product or the unity frequency, because that is where we are interested. We have to find out the phase at this frequency. Okay, this is the frequency axis. So angle V out by V in equals minus tan inverse. Frequency we replaced with gain bandwidth product divided by Z is the first, it is a 0, minus tan inverse gain bandwidth product. We again replacing this frequency with this, because this is the frequency where we are interested. This is the frequency where we are calculating the phase margin, divided by P1 minus tan inverse gain bandwidth by P2. This is also P2. Now we have all these relations. This we already designed, these relations. So we can substitute those relations. So before substituting, we already assumed that the 0 is 10 times the gain bandwidth. So first we can do that. This equals minus tan inverse gain bandwidth 0 is 10 times the gain bandwidth. So gain bandwidth divided by 10 times gain bandwidth, because 0 is 10 times gain bandwidth because of our assumption. Then in the tan inverse gain bandwidth product, we can we have gain bandwidth equal to gm1 by cc. So that we can write gm1 by cc divided by p1. P1 we have 1 by gm2 r1 r2 cc. So we can write 1 by, this is gm1, gm2 r1 r2 cc minus tan inverse, this is gain bandwidth divided by P2. So P2 is gm2 by C2. So gain bandwidth is gm1 by cc divided by P2 is gm2 by C2. So we can write in a simple way is minus tan inverse of 1 by 10 minus tan inverse, here we can cancel this cc and this cc, there is nothing else to cancel. So it is gm1 gm2 r1 r2 minus tan inverse here also there is nothing to cancel. So gm1 c2 divided by cc times gm2. Or actually we are trying to find the relationship between gain bandwidth and P2. So we will we will make this substitution later. So for the time being, let it be GM gain bandwidth product by P2. So this is the angle V out by V in. So I am writing it again. We are not doing this substitution now. We will do it later. So angle of V out by V in equals we are calculating at the gain bandwidth frequency minus tan inverse 1 by 10 minus tan inverse GM1 GM2 R1 R2, that is we are familiar with that. GM1 GM2 R1 R2 is the DC gain, so we can substitute this as DC gain ADC minus tan inverse gain bandwidth divided by P2. We are not substituting the value here because at this point we need a relationship between gain bandwidth and product to get the required phase margin. We have this equation, angle V out by V in equals minus tan inverse 1 by 10 minus tan inverse DC gain minus tan inverse gain bandwidth divided by P2. So now we can substitute these values. Before substituting, one more point. This is the required phase. We record the water plot P1. This is the gain bandwidth, and this is the P2. This is the frequency axis. And we started the phase from 0. So initially it will be 0. So after P1 it will go to 90, minus 90. And after P1 it will be minus 180. So assume we are here. This is our required point. So at this point, what is the angle? So if we started from 0, so the angle, the phase margin is the difference between this 180. Phase margin is the difference between this 180 and this angle. So that we can call it as minus 180 plus this is the PM, phase margin. So at this point, what is the net angle? That equals minus 180 plus phase margin. Or if we are instead of 0, if we suppose we started from 180, then it is a little bit easy. If we started from 180, this point will be plus 90, this point, final point will be 0. So whatever this point, it will equal to phase margin, because see, this is 0 from phase margin, 0 plus phase margin is this angle. But if we start from 0, then final point will be 180. Then what is the angle? Exact angle here is minus 180 plus phase margin. So what we calculated here is minus 180 plus phase margin. Okay, I think it is clear. So if you have any doubt, you can start with 180 and just use the phase margin. So this 180 will not come here. But if you are starting from 180, initially you have to give a 180 here. 180 minus this terms will come. Okay, so I'm just starting with 0 itself. So this angle will be minus 180 plus phase margin. So it should be clear to you, because phase margin is the difference between this 180 degree, how much angle higher than minus 180. So that equals minus tan inverse of 1 by 10, that we have to calculate. That is this tan inverse 0.1 is 5.71. It's minus 5.71 minus tan inverse at DC. So DC gain is generally a higher value. So see, let's calculate. See, tan inverse, suppose the DC gain is just 100, then itself it is 89.42. If the DC gain is 1000, generally it will be higher than 1000. It is 89. So the maximum value that the tan inverse can go is 90 degree. So we can assume that DC gain is a pretty large value and the tan inverse of that is 90 degree. So if your gain is less like 1000, it will be 89.94. If it is less than 1000, like if it is 100, 100 is very low for a op-amp. Okay, even it will be 89.42. So, but you can assume it as a 90 calculation minus tan inverse gain bandwidth divided by P2. So we assume this tan inverse DC gain is 90, and now we can calculate. We can take this minus 180 degree to this side. So phase margin equals 180 minus 5.71 minus 90 minus tan inverse gain bandwidth divided by P2. So it is 180 minus 5.71 minus 90, that equals 84.29. So phase margin equals 84.29 minus tan inverse gain bandwidth divided by P2. So now we calculate what is the condition for a phase margin of 60 degree. So we will calculate that for 45 also. Here we calculate for 45. Here we calculate for 60 degree. If phase margin is 60 degree, you can put 60 equals 84.29 minus tan inverse gain bandwidth by P2. So you can take this tan inverse to this side. So tan inverse gain bandwidth divided by P2 equals 84.29 minus 60. It is 24.29. 24.29. If you are taking the tan on both sides, then this part will be gain bandwidth by P2, that equals tan of 24.29. So this part we will do later. So we can write tan of 24.29 is 0.4513. So gain bandwidth divided by P2 equals 0.4513. Now we want P2. So P2 equals, P2 we can write gain bandwidth divided by 0.4513. So the inverse of that value is 2.2. So P2 is 2.2 times gain bandwidth. So if you want a phase margin higher than 60 degree, you have to make sure that the second pole is greater than or equal to 2.2 times of gain bandwidth. So this is the condition for having 60 degree phase margin. So we have the equation phase margin equals 84.29 degree minus tan inverse gain bandwidth divided by P2. So if we just need a 45 degree phase angle, 45 degree equals 84.29 minus tan inverse gain bandwidth divided by P2. So this value will come as 84.29 minus 45, that is 39.29. So you can take this tan to this side. So tan inverse gain bandwidth divided by P2, that equals 39.29. If you are taking tan on both sides, gain bandwidth divided by P2 equals tan of that value is 0.8181. So hope it is clear. 39.29. Yeah. So for this P2 is gain bandwidth divided by 0.8181. So P2 should be for phase margin 45 degree. P2 should be greater than 1 divided by 0.8181. So it is 1.22 times of gain bandwidth. So if we need a phase margin of 60 degree, we should ensure that P2 is greater than or equal to 2.2 times of gain bandwidth. And if we need a phase margin of just 45 degree, we have to ensure second pole is higher than to 1.22 times of gain bandwidth. But in our design, we are sticking with the 60 degree phase margin. So to ensure that our pole should be 2.2 times of gain bandwidth. And now we are going to the design point of view, like in the circuit point of view, how it will look like. So we have all these equations for 0, P1, P2, gain bandwidth, and the DC gain is already derived. So we will just substitute them. And okay, P2 we have GM2 by C2. So we can write GM2 by C2 should be greater than or equals, this is P2. Gain bandwidth is GM1 by CC. So 2.2 times GM1 by CC. But in this point we should remember that CC is this compensation capacitance. C2 is the output capacitance of the second stage. That means it will be equal to CL. Okay, here in the circuit we put it as CL. C2 by C2 we mean the capacitance of the second stage. So capacitance at this node will be CL. So in the design we will change to C2 will be equal to CL in circuit point of view. And we are here now. So before that, when we are deriving this equation, we made an assumption that the 0 is equal to 10 times of gain bandwidth. So Z equals 10 times gain bandwidth. This equation for 0 also we have. Equation for 0 is GM2 by CC, that equals 10 times of gain bandwidth. Gain bandwidth is GM1 by CC. From this we can cancel the CC and we can write GM2 equals 10 times of GM1. And we can substitute this value here. In that case we will get GM2 by C2. We told that C2 will be CL. By C2 we mean the capacitance of second stage. Really, actually it will be the load capacitance. So we can replace C2 by CL. CL should be greater than or equal to 2.2 times GM1 by CC. But GM2 we can replace by 10 times of GM1 we got from here, by CL should be greater than or equals 2.2 times of GM1 by CC. This GM1 we can cancel, and what is remaining will be 3. So we can cancel this GM1. So what is remaining is 10 by CL greater than or equal to 2.2 times by CC. So we can rearrange it as CC should be greater than or equals 2.2 by times CL by 10. So from this we can make CC should be greater than or equals 0.22 times of CL. So this is the circuit point of view. This is what we have to do to make sure that the phase margin is greater than 60 degree. If we want the phase margin greater than 60 degree, this is the CL and this is the CC. So the CC should be greater than 0.22 times of CL. So this is the condition for phase margin 60 degree. Now we can, I think we almost derived all the equation that is needed for the circuit simulation. I think we can directly go to the circuit simulation now.